Hello, welcome to Group 8's research presentation for design processes and the Nvidia AI board. Firstly, we will discuss the design process, more specifically the engineering design process.
Lastly, here are the references for the NVIDIA AI board portion of our presentation. A lot of our information we got directly from NVIDIA, especially regarding their technical specifications and applications of the Jetson boards. Additionally, we use a lot of third-party articles to go into more topics like ethical issues, additional applications, and challenges that the boards will face in the future. Thank you for watching.
Hello, my name is Francesca Dumari, and in this part, I will be presenting conceptual and preliminary design. So, the conceptual design has 5 points. In conceptual design, you generate multiple high-level concepts, explore solution space broadly, evaluate ideas against requirements, lay out and brainstorm ideas and solutions, and create draft sketches, models, and diagrams. So on the left side in the picture, in conceptual design, you have performance requirements and geometric constraints. Then you try to combine and work these two together, define contributor design parameters. Now as for preliminary design, you narrow down to one concept, define subsystem interactions, ensure design meets requirements, break down design into different sections, find interactions between different sections, and then the graphic preliminary design has introductory basic dimensioning, and then flow with calculations. And then you have detailed design, which has 3D geometry data, then mesh, then CPD analysis. Now we'll talk about detailed design and strategies. So first up, you have system design strategies, structured design, object-oriented design, and then function-oriented design. In detailed design, you define the hardware, software interfaces, and circuits, produce full design specification and cost estimates, verify requirements are satisfied, estimate costs, resources, and timelines, create diagrams and flowcharts, and there are also some strategies. For example, you have least commitment where you delay decisions until justified, problem, decom- problem decomposition, divide into manageable subproblems, iterative refinement, improve design gradually, trade-off analysis, balance cost, complexity, and performance. And finally, have risk mitigation where you plan out issues. Now we'll talk about integration, testing, and performance. So in system development, you would apply top-down design, then bottom-up implementation, integrate components into subsystems, then full prototype, combine subsystems into a complete prototype, verify subsystem interactions and data flow. And as for testing and evaluation, you would add testability features and diagnostics, evaluate system performance with requirements, define success criteria like accuracy, response time, and ease of use, perform unit, subsystem, and system level tests, and then document results and improvements for design. So in the orange graph at the top, you have E2E, which is end-to-end testing, where you would evaluate the program from start to finish. And then you have features test where you test the features. And then integration tests where you integrate components into subsystems. And then unit tests where you verify interactions and data flow. And that will be the end for my part of the presentation. And now we'll pass it on to the next person presenting. Thank you.
How important is teamwork when it comes to design processes? Well, when you work in a team, you are working with people of different backgrounds, different disciplines, such as mechanical engineering, electrical engineering, or computer engineering. And teamwork ultimately allows different perspectives to come about and also to distribute the tasks that have to be completed across the team. And when you have different perspectives, it allows for much better solutions to be made. What if the prototyping process fails after you test the prototype? Well, if that's the case, you will have to go back, essentially from square one, review certain assumptions about the design. You'll have to modify it given what failed exactly after you started to prototype. Then you have to test again. After every test, you need to document the results iteratively to inform future decisions. What are the ways you can handle conflicting design requirements? Well, first you would have to talk to the stakeholder who has input, which would be your client, and you would have to keep in mind aspects of safety and whether or not certain design requirements are even necessary or not. You would have to ultimately employ trade-off analysis to figure out what design requirements ultimately work and don't work with the design process. And also you can employ a filter of criteria to ensure that the decisions that are made regarding design requirements are done transparently. What is the significance of having iterative steps in the design process? Well, iteration is very important because as you work progressively, it allows you to ultimately see if something goes wrong. All you have to do is just backtrack one or two steps. You don't have to backtrack a whole lot. And it allows for refinement of any solution that comes about with the team. And of course, going back, as I'm repeating myself again, going back and seeing how the redesign is a much better improvement over the previous iteration. Models and prototypes sound similar in theory, but different in certain regards practically. How so? Well, when you think of a model is more of a concept, something you draw out, something you put on a piece of paper and think, okay, this is what it'll look like, more of a skeleton of sorts. And that the skeleton just communicates how the design should be. Whereas a prototype, it's something that actually works. It is derived from the design, but it actually works. It's sort of a mini version of whatever you're going to make that ultimately tests the functionality, the performance, and the usability that the team intends to achieve.
My name is Sopaveda, and our next presentation topic is the Nvidia AI board. This outlines the structure of the presentation. First off, we're going to start with defining what the board is. We're going to go into its engineering applications, as well as things like the ethical issues and the impact on society that these boards will have by looking at the three primary Jetson boards, which we'll see in just a moment.
Pushes performance further, making some of the most powerful edge AI computers available today.
The Jetson Nano is the most cost efficient and is useful for power limited applications. It's ideal for embedded environments as well, and it supports real-time inferencing and multimedia applications. And it is the most affordable out of the three boards that will be mentioned. The Maxwell GPU architecture ultimately allows for maximum performance per watt and allows for parallel AI processing. The clustered multi-core CPU complex SMP consists of 4 ARM CPUs, and the CPUs are comprised of the Cortex A57 and allows for multi-threaded computing, and it balances general processing tasks as well. performance monitoring is done via 6 counters present in the CPU cluster that ultimately monitor cache use, instruction count, stalls, and it's really useful for optimization and debugging. The HD audio video subsystem that offloads audio video processing from the CPU, which thus allows faster concurrent operation, and consists of the multi-standard video decoder and video image compositor, is critical because in vision-based applications, when there's a camera, inference both have to happen in real time. The image processing is done via the image signal processor, which is very important because it enhances any quality that you might need before using AI inference. And it doesn't use GPU or CPU resources as well. And the display is controlled via a complex of 2 controllers, and the memory consists of 4 GB LPDDR4 in conjunction with a controller that maximizes memory utilization. The second board is the Jetson Xavier, which is the second most cost efficient and useful for a wide array of applications. It's a balance in between the 3. The memory that is present is that of the LPDDR4X at 64 gigabytes. The GPU architecture is the Volta GPU architecture that contains streaming multiprocessor that is optimized for deep learning applications and is more energy efficient, which is very important in autonomous systems. Dual-core CPUs are clustered in the Carmel CPU complex that allows for simultaneous multi-threading / processing, which is great for handling parallel tasks efficiently. The display is controlled via a unified display controller, just similar to the previous board. The HD audio video subsystem is again comprised of 2 of each of the multi-standard video decoder and encoder, JPEG processing block, and video image compositor. And also, the display controller reduces the CPU load for display management. Also, security is emphasized as there is a security controller that allows for the authentication of code via secure boot ROM and signature verification keys, as well as a security engine that contains RNG to seed random bits. And it also contains a deep learning accelerator that is utilized to accelerate inference operations on convolution neural networks, which essentially speeds up AI tasks without taxing the GPU or CPU resources. And the last but not least is the Jetson AGX Orin, which is the least cost efficient of the 3, but the most powerful of them all. It is suited towards deep learning and AI applications, as it has a deep learning accelerator just like the Xavier. The Ampere GPU architecture is composed of 2 graphic processing clusters, which help deliver a massive GPU computations for vision and inference tasks. And it gives, compared to the Xavier, superior parallel processing capabilities, which makes it ideal for AI inference and high-resolution image processing tasks. The 3rd generation tensor cores are improved and implemented upon to accelerate AI applications, which ultimately, of course, it makes AI matrix operations significantly faster, and it'll accelerate deep learning inference and training. The Deep Learning Accelerator 2.0 is improved upon from the Xavier, allowing for increased local buffering and reduced DRAM bandwidth, along with a new set of features. And, of course, allows for more efficient inference. The CPU architecture is that of the Cortex A78AE that consists of 12 CPU cores, which makes the Orin twice as fast as the Xavier with its Carmel CPU, which is very, very important. The memory bandwidth is 1.4 times that of Xavier and is double the memory capacity and storage, as 32 to 64 gigabytes of LPDDR5 and 64 gigabytes of eMMC storage is supported. And of course, that's important because as AI models continue to get bigger and data sets continue to get bigger, you need something very powerful to process that. Orin also contains a multi-standard video encoder and decoder like the previous two boards, and the image processor supports the programmable vision accelerator PVA engine and the video imaging compositor 2D engine, allowing for computer vision applications and processing features including such as lens distortion correction and enhanced temporal noise reduction, as well as various image processing improvements such as sharpness enhance and general pixel processing such as scaling, blend, etc. This is ultimately great for computer vision models that need to be done via AI.
So I would like to map out the relevance of NVIDIA AI boards for engineering designs by some examples. The Jetson AGX Xavier, for example, was a breakthrough built on volatile architecture, delivering up to 32 tops and 32 gigabytes of memory, making it ideal for multi-sensor robotics and navigation tasks like SLAM. Building on that, the Jetson AGX Orin took things even further with over 200 tops and up to 64 gigabytes of memory, enabling applications like computer vision, natural language processing, and even on-device LLMs. Now, these boards are so relevant for engineering design that they combine high performance with accessibility. Unlike traditional uh, processors, NVIDIA GPUs are used for, like I said earlier, parallel processing and deep learning. Um, these capabilities mirror how our own visual cortex processes compute complex information, and they allow engineers to quickly develop and deploy AI models for real-world applications. So when we put this all together, the Jetson family represents more than just hardware. It's a platform that bridges research and real-world engineering. So we might encounter some issues with the NVIDIA AI boards. So let's dive into some of those. On the hardware side, these boards can draw a lot of power and produce a lot of heat, especially when they're pushed to the limit. Smaller boards such as the Jetson Nano also run out of memory limitations. They basically run out of memory, that's what I mean. And even NVIDIA themselves have faced issues. For example, when they used a RDL interposal with local silicon, they tried to interconnect bridges to push transfer speeds up to 10 triabits per speed. The problem was thermal expansion. The GPU chiplets, the interposal, and the motherboard didn't expand evenly with the heat, which caused warping and failures. NVIDIA actually had to redesign the top metal layers and bump structure on their GPUs to fix that. Next issues you might encounter is the integration. It's not always easy to connect these boards into real world systems. Sensors and peripherals don't always play nice, and moving from a prototype in the lab to a large deployment can be really tough. So there's also software and development as well. Even though NVIDIA gives us tools on their website like CUDA, TensorRT, and Jetpack, there's still a steep learning curve. Debugging AM models is complex, and optimizing for for the performance can be very complex and take a lot of time. And finally, the costs. The boards aren't cheap. High-end Jetson modules like Xavier or Orin, like I said earlier, can run into thousands, which makes it hard for smaller companies or schools to use them widely. Let's talk about some of the challenges and opportunities that NVIDIA AI boards have. So some of the challenges is about NVIDIA as a whole, and especially the boards as well. So the first big issue is the product roadmap visibility. Many of the NVIDIA's biggest customers, like the large cloud providers, are frustrated because they don't know what the company's future chips will look like. Second, there's a problem with over ordering to make sure that they get enough supply. Some companies are ordering way too many GPUs than they actually need. That inflates today's demand, which also raises the risk of sharp drop once AI training levels off, which analysts expect could happen um, within the next 12 to 18 months. Third, there's been many concerns about the growth beyond 2026. Nvidia has been riding a wave of success, but insiders admit there's anxiety about what comes next. They'll need another major breakthrough to keep momentum, and there's no guarantee what will happen next. Finally, there's a paradox of AI itself. Research in AI is moving so fast that even NVIDIA risks falling behind. New neural networks are becoming more efficient and powerful at a pace that challenges hardware to Keep up. So when NVIDIA is leading now, they're under constant pressure to stay ahead. But on the flip side, there are huge opportunities. NVIDIA AI boards itself enable real AI at the edge in robotics, computer vision, and even speech recognition. In systems like automotive systems, they have drones, self-driving, and even SLAM, self-driving as in like Tesla that we see today. Um, we also see an edge with LLMs and NLP. Um, we're seeing AI boards power on-device copilots and voice assistants, reducing reliance on the cloud. So overall, while the challenges are real, the opportunities show why these boards are becoming essential in the future of engineering and AI.
We can look at the applications for the three primary Jetson boards. To begin with, the Jetson Nano is the most affordable and attractive board for beginners, hobbyists, and students. This is because the board is very compact and has a pretty low power consumption, making it suitable for smaller and space constrained projects. But despite its size, it still has more than enough computing power to handle tasks like image tracking, object detection, and basic AI inference. In regards to the AGX Xavier, it is overall a much more powerful board built for serious robotics and industrial projects. It's great for things like drones, delivery robots, smart manufacturing systems. So it's something that you're going to see is associated with a lot more commercial use. And it supports multiple sensors and high res cameras for these complex perception tasks. And now we can take a look at the AGX Orin, which really is the powerhouse of the entire Jetson family. It's built for advanced self driving cars, smart medical devices, and high end robotics. It's known for being able to power really heavy AI workloads, things like deep learning, computer vision, language processing, etc. Even though it is extremely powerful, it is still also compact enough to be suitable for real world projects. Ethical issues regarding AI are very numerous, but the thing with AI boards is that it makes this AI computing technology accessible to basically anyone who can afford it. This creates overall more opportunity for the misuse of this AI technology. It can be used for things like deepfakes, rogue robotics, automated surveillance, and more. These are all technologies that really push ethical and legal boundaries. And of course, as more AI technologies automate everyday tasks, some jobs could be at risk. This basically forces business to make a tough choice to adopt AI to cut business costs and make these processes more efficient, or to protect these jobs and avoid layoffs. With AI being such a powerful and accessible tool, they can also be considered critical infrastructure. The more computing power, the more potential for military and strategic technologies to expand. That is why some countries like Russia and China face restrictions on importing certain boards. We are heading towards a more technology advanced world, and this technology is becoming more of an asset that certain countries are looking to protect. Additionally, AI models built with these Jetson boards learn from the data that they're trained on. And a lot of these data sets could have bias. So the model set up on these boards could pick that up too. This can lead to things like unfair results, like favoring certain groups over others or making inaccurate predictions based on race, gender, age, etc. And this overall is a big ethical concern because this is something that could motivate hiring practices, policing, or healthcare technologies. In regard to the AI board's impact on society, it'll make AI technologies more readily available, not only affecting our workplace and the technology field, but how we live our everyday lives. In regards to job market shifts, of course, there's a good chance we're going to see a lot of these routine jobs be taken over by AI technology and things like robotics. That will also open up a lot more tech related jobs since people are needed to build and maintain these systems. In healthcare, AI is helping doctors diagnose diseases more accurately, as well as helping them discover new drugs faster and being able to personalize treatment plans. So it's speeding up a lot of processes at unaccounted for rates. In education, AI tools are also making learning a lot more personalized. It can be argued that everybody can now have a personal tutor through things like chatbots and even more AI technologies. This will also be great for students with disabilities or those who work in remote areas, for example. Regarding economic growth, AI is boosting productivity by automating tasks and opening the door to entirely new industries that we haven't seen before, like autonomous systems, smart devices, and synthetic media. In regards to public safety, AI is now helping detect threats, responding to emergencies, and predicting risks before certain events even happen. It is currently being used in things like surveillance, disaster response, overall increasing public safety. In entertainment, AI is changing how we create and consume content. We're seeing a lot of AI generated music, art, uh, personalized recommendation for these media, and that also actually raises an ethical concern with certain artistic related roles being overtaken by AI. In regards to transportation, AI also powers autonomous vehicles. It can help optimize traffic flow and improves logistics, making traveling safer, faster, and more efficient. To wrap things up, here are a few questions to help you review and reflect on the topics that you learned here today. The questions are: what distinguishes Nvidia AI boards from traditional microcontrollers? What are some common challenges when deploying AI boards? Which Jetson board is most powerful and best suited for deep learning applications? How does the Jetson Nano differ from the Jetson AGX Orin in terms of performance and use cases? And what opportunities do AI boards present for future innovation? In order to keep our group organized as well as maintain a central hub for all of our research, we decided to use Microsoft Teams. Teams made it super easy to, of course, create a group with all of us in it, but also organize the files that we needed for this project, such as you can see below the meeting summary. We also included links for our Google Docs files where we could bounce ideas off of each other as well as include research. We also used the planning feature to make sure that we had strict deadlines so that we could, in the end, collaborate and combine all of our work, of course, into this presentation that you are seeing now. Lastly, here are the references for the NVIDIA AI board portion of our presentation. A lot of our information we got directly from NVIDIA, especially regarding their technical specifications and applications of the Jetson boards. Additionally, we use a lot of third-party articles to go into more topics like ethical issues, additional applications, and challenges that the boards will face in the future. Thank you for watching.